Hello everyone, welcome. Today we have Ekin, and he will give us a talk in context language learning and endurance here. So Ekin is a PhD student at MIT, candidate, and he's studying generalization in neural sequence models advised by Jacob Andreas. He wants to understand how learning and algorithmic reasoning works in language models and use this understanding to design better models. His early work aimed to enable neural sequence models to compositionally generalize new tasks by a small number of demonstrations. And his recent work contributed to understanding of how transformers do in context learning in model problems like linear regression and formal language learning. And he is a recipient of Amazon Alexa Fellowship and Area Chair Paper Award in ACL 2023. He received his bachelor from EC in physics from Koch University. And we are very happy to have him here with us. So yeah,
thank you for this full introduction. Thank you for coming here today. Today I will discuss a little bit what is in-context learning and propose a new model for in-context learning. And then we will uncover how transformer models learns new structures in context and why they are better than other sequence models. And then we will show how to use this analysis to improve transformers even further in language modeling task. Okay, so let me start with a real story for in-context learning. Last year, February, we had an earthquake in my home country, Turkey, and it was devastating. Like everyone was posting their emergency needs on the Twitter. And a group of people realized that we can use this data to save more lives. And I joined this online group that night, and they were developing various applications to help people in need. And one of them was extracting needs and addresses from the tweets that people put, so that the NGOs that are on the field can use this map to reach out to people. When I joined, the pipeline was already implemented. They crawl all the tweets that matches certain keywords, and the domain experts provide some labeling instruction. And volunteers sit down and label thousands of tweets. And finally, we fine-tune a BERT model to classify the rest of the tweets. But the challenge was, every hour after earthquake, people need different stuff. As a result, the target labels that we use constantly changes. For example, after a day, oh, sorry. So, for example, after a day, you need to identify who needs stents. And sometimes the initial labels are too coarse, so you need to make them fine-grained. Okay, so basically the labels are changing constantly. So this existing pipeline was actually very costly, because every hour or so, we need to label thousands of tweets again, and we need to find a new BERT language model. So also using BERT language model sounded like in 2019. And instead of this, I simply suggested prompting large language models with few examples from this task. And whenever new labels come, I just write down a prompt like this with few examples from this classification task. That is basically the instruction itself. And then we annotate the rest of the tweets by using OpenAI's GPT model. And this worked as good as the previous pipeline. And that was kind of amazing, because after this, we spent literally no human hours for the machine learning part. So if you look back this from a scientific point, it's really hard to grasp how this is possible, right? We somewhat replace whole model training pipeline and labeling pipeline with a single prompt. So the main question of my recent research was to understand how this works, how a single frozen language model like GPT can learn many different tasks instantly without any additional training. And this is called in-context learning in the literature. But is it really learning, right? Language models are good and expert predictors, and they are just good at completing anything, and probably so many similar examples during training. So why do we call this as learning? So we'll make it a little detour. I think it's important to discuss this, and it's important to discuss why do we call it as learning at the first place. What is actually happening here, right? So we have a large language model trained on whole web data train complete next document in every document you can think of. And then we just provide few examples from a task like English to French translation or semantic labeling or even polynomial regression. And language model can complete all of these different prompts correctly. But if you look at this from language modeling perspective, these tasks are common on the internet, right? Language model is just doing next word prediction as usual. So maybe one hypothesis for in-context learning that is not actually learning. It's just memorization of individual examples, if not memorization of tasks that the model already know from pre-trained. And this statement is obviously true that we can teach translation with just 5 examples. But when you look at other tasks, that is not common as the previous ones. For example, the ones you can generate synthetically with arbitrary vocabulary or structure, like this string puzzle here that I just created for this presentation. Or in-context lookup examples with arbitrary mappings of characters and numbers. And this is sometimes called associative recall. Or recently, Google's Gemini model showed that it can somewhat learn a very, very low resource language called Kalaman only from a grammar book and lexicon directly. And this is a lot to grasp and say memorization to. But you can still argue that GPT might have seen similar examples and tasks in the internet data, and maybe with slightly different structure and vocabulary. However, with this statement, you actually acknowledge the learning is involved, right? Because what is learning? If you think k-nearest neighbor algorithm, it exactly works based on similarity. So if you buy this statement, you can already entertain there is some primitive learning involved based on similarity. So in my previous research, I pushed that we should actually accept the learning hypothesis that these models can simulate learning algorithms in context. Because only then we can ask how unsimilar tasks they can actually learn. What is the generalization properties of these models? What learning algorithms they can implement in theory? And then you might even go further and ask, how can I improve the algorithm that the current language models do? Or how can I extract an algorithm from this giant model and use somewhere else? So there are many more fruitful questions if you go this path. So, and today I will show some examples of these. But how do we study this, right? Probably the algorithm language models implements are complex, and we don't know what the model memorized from pre-training and what it actually learns in context. And it is expensive to replicate language model training and do controlled experiments. So what can we do? And biologists already developed a way to study complex systems like us by introducing model organisms. Because they can experiment with humans, they had to work with these simpler models. And as AI researchers, we are in a similar situation. Language model pre-training is hard, and even if you can't run multiple controlled experiments. So we may also come up with model problems to study certain behaviors, such as in-context learning. But what makes a model organism nice to study, right? So they need to be reproducible across labs. They should have rapid life cycles so that you can experiment fast, and they should be in small size. And most importantly, we want these problems to look like, to have some similarity to humans. So what is the analog for us? We want problems easy to train. We want small models to achieve non-trivial success. And we want structural similarity to real in-context learning examples that I showed. And machine learning folks already came up with this. So maybe because it's the simplest problem in machine learning, and we know a lot about linear regression, people were really interested in in-context linear regression as a model for in-context learning. And I consider this as like C elegance of ICLL. And let me briefly introduce this problem. Remember the few-shot translation example, and this is a single word version. And the model presented examples from a mapping, and in this case, English to French, and it needs to figure out this mapping. Now, instead of this, in the linear regression problem, we asked if we can build a model that can observe sequence of input-output pairs exhibiting a linear relationship. And we want this model to infer this relationship on the fly or in context. And by the end of this sequence, do a good job of predicting y's from x's. Note that we want model to in context on any linear function. It's not just memorizing a single linear function. Why do we do this? Because we want to test this hypothesis, right? Whether a frozen LM can learn a new linear function with few examples. And with this simple linear function case, we can study in-context learning in isolation with small models and small data sets. So when studying these problems, we train a transformer language model from scratch on some example problem instances. We first create a training set or meta training set by sampling different linear functions from some distribution. And for each linear function, we create an example problem instance by sampling points in hyperplane. And these points will be our few-shot examples. Then we will train this transformer to predict the next vector, given previous vectors like language models. And we will check whether outputs gets close to the ground truth after seeing enough number of examples. And once you train with this with a good number of problem instances, you can actually show that a very small transformer can learn this optimally. They actually discover least square solution that we know from high school. And this model sparked a theoretical curiosity. Many people, including many people here, perform different analysis on transformer models, such as convergence, training dynamics, and phase transitions. But you may wonder how this relates to the actual language models that works with real language inputs, right? So here we have continuous inputs that are completely different than the examples that I showed. So people suggested another model, sometimes called associative recall, which looks like more language. So here we ask model to learn a simple map from the examples on the fly, and we create this map randomly. And you can think of this as a phone table where each number matches with a person, and the model needs to copy correct number when an existing name appears. So here, like after seeing A, second time it should output 7. And this is a very simple task used to evaluate recent state space models and alternative architectures to the transformer model. And here again, we create a meta training set with random mappings, and then we create training examples from these mappings. And then we train a transformer language model to predict the next character given the previous characters. And we then test the model's ability to learn completely new mappings. So like in the test time, we ask like other mappings that is not seen in the training time. And again, previous research showed that transformer models can do this perfectly, like whereas RNN models can't do well. So okay, these problems show transformers, in theory, in context learn novel functions and enable control studies. But are these problems structurally similar to actual in context learning examples? First of all, they have non-structured inputs and outputs, right? Each input output is either a single token or a single step in these problems. But machine translation or any other complex examples that I showed earlier will have multiple tokens in the input and output. Second, these model problems do have deterministic transition functions. Each output is a deterministic function of the input in the ground truth data. But the real in-context learning and language in general probabilistic, right? So for example, we might have multiple translations for the word cheese, and this is true for any other task that includes natural language. So our model problems come from structurally different generative processes. So what should we do? And in this work, we realized that we can close this gap by using in-context formal language learning as the model problem. And we can also show that this is generalization of some of the problems listed here. And we will show this in a bit. In this problem, we ask model to learn how to generate strings from formal languages in context. Unlike other problems, the models here need to learn generative processes instead of a deterministic function. So let me explain this a little bit more. Each example here belongs to a unique probabilistic language. When I say language, it just means this simple finite state machine or finite state automata with probabilistical transitions on the edges. If you saw this first time, I think I can just go over a little bit. So let's say there's some start state, like 1, and you can take an edge from this state here on the edge is A, so you produce the character A, and then you end up with state 3. And from here, you can either take the character D or character C, and with equal probability. And with this way, you can generate this sample, right? You can generate another sample, and you can generate another. And this will be our examples in this task. And with the regular languages case, we have already what we wanted, right? So we have structured samples that comes from a probabilistic generative process. And because of this, it's a probabilistic transition. So we don't have deterministic transitions. And we will train again language model from scratch on this task to predict the next character as usual. But to succeed in this task, language models need to infer this state machine on the fly from the previous examples sampled from this machine. So they need to infer this structure. Similar to the previous task, we test these models on completely disjoint test languages or state machines. None of the test languages or strings will be seen by this model. So any memorization strategy can make you fail in this task. And it's 100%, you will see completely different character sequences. And the model needs to implement some language learning algorithm here. And we evaluate these models based on how well their next token distribution matches the ground token next token distribution given by this structure. And we will use total variation distance, which is this L1 distance between two distributions divided by 2. Okay, so I define this need problem and explain. Okay.
In finite automata, there's usually like some kind of accepting state.
Yes.
Do you have
So these are like called like non-accept, like the probabilistic finite automata without accepting state. So they can assign infinite length probability to infinite length strings, and we use them as like our structures. So we don't have any end state.
So as long as you're following this like probability
Yes,
distribution,
yes.
you can.
Yeah, you can also think them as hidden Markov models. So they're equivalent to hidden Markov models. Yeah. Okay, so before going to results, I want to show two subsets. We already saw this one, right? So any associative recall example actually subset of in-context language learning with regular languages. For example, for this example, we can construct this finite state machine where each key maps to a value, like the value that is presented in the example. And this will be a finite state machine, and that will create the same examples of the associative recall. And you can also show another task, like there's this recent paper called Repeat After Me. So where they test models' ability to copy strings. So here you give this as a prompt to the model, and you ask model to like generate these copy. And you might think this is a silly task. It's very easy, but transformers do very well. But Mamba model, for example, fails in this task if you have very few training data. This is also a subset of in-context language with regular language, because every language with single element is regular language. And here the language has only this element. So we can discuss this more, but like all of this to say like this generalizes this tests and have like kind of like harder tests than this previous ones. Okay, so I show how this new model problem captures the features of in-context learning and how it relates to the previous benchmarks. So I will stop a little bit, like maybe 30 seconds, and to get some questions, then we will go to the actual results and analysis. So let me stop 30 seconds. If people have any concerns or questions, discussion points, we can have some discussion.
Yeah, do you mind kind of explain the main difficulty with like the difference between associative recall and the copying task? Because it feels like for me they're all kind of storing the knowledge from the previous context, but apparently they have some different performance, say for models like Mamba, and it does have some difference, but why,
actually,
where does it come?
That's a very good question. I think after this talk, probably we'll have more idea on that. But in associative recall, you need to match one token, right? Whenever, let's say I see A, I look at the previous context and I find the previous A, and then I copy the token next to it, right? But in this one, you need to match actual, like maybe 3 grams, 4 grams. Like you can't just match A and copy to next token, right? So for example, I could have AB, AC, AD, right? So I can't just, look at the previous A and then copy any of them, right? So I need to selectively find.
I see. So kind of the story scale is the exponential of the.
Yeah, I'm not sure there's something exponential, but basically the n-gram that you need to keep look at gets higher. It's harder fast.
Okay, thank you.
Next question.
Yeah.
So what's the main difference between the sheet paper, the explain constantly new foundation?
Yes, yeah, so like there's another paper that uses hidden macro models. So in that, like the training data is a mixture of hidden macro models, and in test time you need to figure out same hidden, like one of these hidden macro models.
What's the main difference?
Yeah, here, like every time you need to figure out a new language, like new hidden macro model. It's not from the mixture that you saw.
Oh, it's one macro model.
It's like every time you get to see a new macro model, you never saw them in the training time.
Every time
Yeah.
we see. So then during training, how many macros?
Like let's say you see like 1,000 macro chains,
Mhm.
but it's not macro chain, but anyways, let's say macro chains. And they're completely different than the test macro chains.
Oh, that could be different. Oh, I see. Then during pre-training, each string use one markup chain, right? Use one. So
Yes.
I assume different sequences, different markup.
Yes.
During
Yes.
pre-training.
One.
Do you think the markup chain, we should have infinite markup chain? I mean, the state of the markup chain, the number of states in the markup chain should be infinite. Because I can ask, my question can be, what's the token before 100 tokens? What's the token before 100 tokens? What's the token before millions of tokens? In that case, we need the infinity state to identify the token. So I wonder.
I'm not sure if I understand.
Oh, sure. Okay. Sure. Let me repeat my question. So, assuming we only have finite state.
Finite, yeah. So like all of these, like for example, the macro models here are
Yeah,
finite.
we have finite state, and each state will go to another state via some tokens. Assume the number of possible tokens are limited. We have
Yeah.
finite tokens. Then, if I can have infinite question such as what's the token before 100 tokens? So what's the token before? What's the token before 200 tokens? What's the token before 300 tokens? What's the token before millions tokens? That means if I want to solve that, I need an infinity number of states to answer the question.
Okay. So yeah, maybe we should discuss offline, but I think one thing, like you can generate still infinite length strings with finite number of states,
Yep.
right? So yeah, I'm not sure if I understand that, like, that's like, look at like 100 tokens back, like some stuff.
I just feel like if only with finite token, I cannot answer this question correctly.
Yeah, let's discuss like after talks. I want to understand more. Sorry, but yeah, okay. So let me move a little bit to the results. So we have exciting results. So at the end of the day, so we want to show this benchmark is actually useful, right? So like because there are like other benchmarks that we propose something. So in the rest of the talk, we'll first show how can you use this benchmark to differentiate in context learning power of different neural architectures. Like we will compare transformers to other alternatives. And we will uncover why transformers are very good at this task and how they solve this problem. And after these analysis, we will show how to improve transformers even further, and not in just in-context language learning tasks, we will improve them in actual language modeling tasks. And let's look at the transformers results, so in-context language learning. As I mentioned before, in the y-axis, we measure total variation distance between models next token distribution and the actual ground truth distribution. And we report the average of this over all examples in the test set and all tokens in my test set. And we do this experiment for different number of training examples in the x-axis. So, and then we get this learning curve, right? And now we will step by step contextualize whether these numbers are good in absolute sense, right? First, we will compare transformers to other models. And later in the talk, we will compare transformers to some historical algorithms that can do language learning. Let's first compare it to the linear transformer. And there's an alternative called RedNet, which is also a linear transformer. These models do not have softmax in the attention module. And as you can see, if you just remove the softmax from the attention, you immediately get significantly lower results. And we can also look at modern and popular recurrent models like Mamba, and there's another one, GLA from MIT. And we find that they perform similar to the linear transformer, but maybe Mamba is better in low resource. And convolutional state space models like Hyena or H3 performs worse than any linear transformer. And S4 is the worst model here. S4 result is kind of intuitive because S4 here is the only linear time invariant model. If you write the recurrent form of these models, it's the only linear time invariant. So it can have like less expressive capacity for such a task. And there's also like good old LSTM models in NLP literature, similar to H3. They kind of perform to similar to H3 model. And as a result, somewhat transform is best model here. But what will happen if you did the same experiment with the associative recall task, like this simple task that I showed earlier? As you can see, the differentiation between transformer and other models are less clear here, right? And one of the issues with this task, it's actually quite simple in absolute sense. For example, if you did pick a static number of training examples, like 5,000 here, you can very quickly hit to the full accuracy. And you may even misconclude that your model is as good as transformer. And this is kind of very common issue with many previous state space papers in the field. And moreover, there is a 2-gram model, which does like the thing that I explained here, like copying, like by looking at the previous match. I will explain these n-gram models in the talk later, but it can solve associative recall in 100% without any training. So all is to say,
Can I ask?
Yeah.
Do you test this model in for different input lengths? Like, let's say you train it up to 100.
Yeah.
Do you also test it up to 100, or you also test it kind of out of distribution?
Yeah, we always did the in context in this paper, but I think it's really exciting to do out of distribution test. So basically, it was always the like some maximum length, we up to that length. Yeah.
Because I think, like, my guess is that it won't perform that well, and then it's kind of interesting. Like the 2-gram will always perform the same independently of the length.
Exactly. Yeah, I think so. In the later of talk, we will develop these hybrid models. I think they will generalize probably out of distribution. So we should actually have done that maybe for camera ready of this paper. Yeah, that's a good suggestion. But all of this to say, these neural sequence models have actually different powers for in-context learning, and you just need to apply a correct test. So we saw these relative performances, but we still don't know whether these models collectively perform good in absolute sense. So we need some baselines, right? And in this section, we will compare best model from these results to some known algorithm for language learning. And in parallel, we will try to understand what learning algorithm transformer actually implement internally. So what makes it better than other models? So if you want to solve this problem algorithmically without using any neural model, you could like resort to a Bayesian approach, right? Each example in our data set is a unique language learning problem with a mini data set. And the optimal algorithm would be to compute this Bayesian posterior probabilities and predict accordingly. But to do this, you need to compute all possible languages that assign non-zero probability to the current input. So like you have this, you have this sum here. Oh, okay. You have the sum here, which is like very, very large sum. So it is kind of infeasible to do this summation. And I don't know any dynamic programming algorithm that can do this. So instead of this, we resort to the heuristic algorithms that we know from NLP literature. Given the current input, we can count the n-grams and predict the next token with the n-gram. If it's first time hearing the n-grams, what we do is keep the count of unique substrings up to length n. And based on the frequency of those substrings, we calculate how likely the next token is. And it's a simple count-based model. But we also know these regular languages are more complex than n-grams. So instead, we could fit a hidden Markov model, as we discussed earlier, and apply a learning algorithm called bound batch. And there's actually one-to-one correspondence between probabilistic regular languages and hidden macro models. But this Baum-Welch algorithm doesn't guarantee any optimal global optimal solution, so it might still perform badly. And note that the difference here between algorithms and like the neural models, these algorithms do not have access to the training data, like the meta-training data we generate. We just ran them on each example separately. So they are our baselines. We surprisingly find that the best algorithm is a simple 3-gram model here. It's even on par with Mamba model, who is trained with lots of data points. And second best is Baum-Welch, and then we see 2-gram is actually significantly worse than 3-gram model. We also see that many of the state space models worse than this 3-gram model. And the most importantly, transformer here is doing something much, much better than any algorithm. So our next question is to understand what transformers is actually doing. In all of the plots so far, we look at how each model or algorithm is close to the ground truth distribution, right? To get more intuition about what transformer and their solution is, we could actually look at distance between the transformer's outputs and the outputs of an algorithm. So we can compare them pairwise. And that will tell how close transformer to that algorithm in terms of output distribution. And in the heat map, you see the numbers, like the distances between the outputs of a transformer and algorithm, as well as the ground truth distribution. So the lower is better here. If you look at the lowest numbers here, you'll find transformer is really close to the 3-gram model, and it is closer than Baum-Welch model. And it is even closer than the ground truth. So like if you look at distance between transformers and 3-gram, it's 0.21. If you look at ground truth versus transformer, it is 0.36, which is higher. So it seems like transformer is more close to 3-gram than the ground truth distribution. But we know it's not exactly the 3-gram, right? So we came up with this hybrid model where we use n-gram counts as features and feed it to a multi-layer perceptron model. So this multi-layer perceptron model will be learned from the training data. So you can take this as a hybrid model. So it's not algorithm anymore. It's a learned model. And it's a learned smoothing over raw n-gram model. And we see that if you use this with normalized n-gram features, this actually approximates transformers better than any other candidate in this heat map. So maybe transform is doing something like counting and then smoothing that counts with some learned mapping, which is learned from training distribution. And another interesting side result that we find, actually shallow transformers are more close to the lower n-gram models. Like for example, 2-layer transformer is best approximated by a 2-gram model, whereas the large transformer that we showed is approximated better with 3-gram model. So we did this experiment to understand a little bit better, right? So somehow transformer close to the counting-based n-gram models, but do they really implement these counters internally? And where are they? Can we find them? So can we understand more mechanistically what the transformer is doing? So we will perform a neural probing analysis to understand if these n-gram counters is actually calculated in the model's hidden layers. If you hear neural probing for the first time, let me briefly explain. So we save the intermediate hidden outputs of a transformer model. Then it's running on in-context language learning examples. So when we feed the inputs, and then we save the intermediate hidden states. Then we try to feed a small MLP model, which is the probe model here, that takes these hidden vectors and tries to predict a target quantity. And in this case, targets are n-gram counts or n-gram frequencies. Sometimes I'll call normalized n-gram counts, which is like the frequencies. And in this specific example, let's say we are asking to predict 2-gram counts, and the query is the query is AB. So sorry, the input is AB, and the query is AB. So and we are at the third time step, like we are at here. So how many times AB appears? It appears 1 time, so the target should be 1. So this is like the probe's aim to predict these quantities. And we train this with many examples and many hidden states from training set, and then look at the test performance. Like, can it predict this n-gram counts from the hidden states of the model? And we did this for many layers, like many hidden states of the transformer and with many models. And we like put the best results here. In the y-axis, you see the error of the probe. The lower is better here, like it's the percentage error on the target. And in the x-axis, we see different models. And sorry, the colors are different models. And in the x-axis, we see like 1 gram count predictor and 1 gram frequency predictor. And the headline result here is transformer and linear transformer had the lowest error than any other model representing 1 gram counts. So it seems like everyone, sorry, like the transformer and linear transformers somewhat count the unigrams, like the every characters, like how many times I saw a character. But the other models seems okay at the like normalized counts, but not in the absolute counts. So there's something like the counts that these models are not good at. And if you look at even higher order n-grams, like 2 grams and 3 gram counts, we see that transformers are much, much better than any other model, representing 2 gram and 3 gram frequencies, like the normalized ones. But when you look at the counts, I think all models are kind of struggle in the large n-grams. So with this analysis, we argue even further that maybe transformers are success are coming from these n-gram counting operations. So probing told us kind of like strengthened our arguments, right? But it doesn't tell exactly what's going on. So can we look at even more mechanistically? Yeah.
So if you go back to the previous slide, but it also seems like the number also works well, right?
In the 2 gram normalized?
Oh, 2 gram and also 3 gram. The number is the dark green.
Yeah, in the 3 gram counts, right? It seems good. But in terms of relative error, it's almost 1, right? So basically, if let's say my target is 3, it predicts 6, right? So basically, like, so I will say all the like numbers here is actually not good, so that they don't represent maybe counts, or there's some issue with our probe training. So that might be, so basically, in these like results, you should always take it with grain of salt, because like we train a neural model to predict these quantities. Maybe our training schema was wrong, so like there's some issues, but it gives you some high level intuition of what is going on. Okay, so can we do more mechanistically, right? Can we understand like exactly what's going on here? So we turn into the attention maps of the transformer. Here we visualize the attentions of 8-layer transformer. I picked some of the layers, and heat maps tell which tokens in the input attends which tokens in the previous context. So like from is like we look at the like which token attends, and so for example, this shows D attends the token N here. And when you look at layer 2 and layer 3, what you see is kind of boring, right? So like all of the tokens attend to the previous token. So it is like, it's not just diagonal, it's sub-diagonal, like just offset 1. So, but when you look at this layer 5, you see some interesting sparse attention pattern. So let's look at more closely. We zoom into a specific row and columns in this attention map. And it's a row that tells where this H character, like this H character, attends to. And what we saw, it selectively attends tokens that has 2 gram match. So the H attends to this token because it comes after NH. And if you look at the other attended token, it also comes after NH. And it comes after NH, comes after NH. So basically it attends tokens that has the same prefix, that has the same 2 gram prefix. And we find this in almost every model. Like we train 12-layer transform. We can always find 1 layer that does exactly these n-gram attentions. And this is true for other examples too, right? So like here I just show 1 input, but you can like try this on different input. You'll always see layer 5 does this job. We can statically formulate, like we can write like what this is, right? So it's basically, it checks every prefix up to n-gram, and then it's also causal, like it's like nothing is bigger than 0 in the upper diagonal. So you can basically write the formula for this attention. And if this is something useful, so basically we kind of identified what's going on here, right? So we find like how it does the n-gram match. So we actually more like mechanistical analysis, but like just for this talk, like basically we find like how this model does the n-gram matching, right? And if this is something useful, to solve ICLL, like in context language learning, maybe it's something useful in general, right? Maybe we can use this pattern for other tasks, right? So what we did is we actually changed the attention layer of transform. So we propose a new module, which is simpler than attention. So first, it has a static attention map calculated by this formula. So it's a very sparse attention map, and it only has one transformation. So this is the what we call n-gram heads or n-gram layer. And the kind of
Okay, so I'm just wondering because I mean at the beginning of the slides you mentioned that the transformer works the best in terms of this task you propose, and other models such as linear transformer and non-body doesn't work well. So I'm just wondering, have you ever performed some similar analysis to this on linear transformer or other models?
Yeah, so in linear transform, because attentions are not normalized, it's hard to understand, if some attention is bigger, basically, it was very uniform. Like when I look at the linear, but when I look at the linear transform, I think it was kind of uniform. It's really hard to understand what's going on.
Oh, okay, I see.
Yeah.
People was just.
Yeah, we did some interpretive. We look at, for example, PCA maps of hidden states to do other attention, other analysis. But seems like this is the only thing we kind of find exactly what's going on. But for other models, it's kind of complex.
I see. So,
Okay.
yeah, do you have any idea or interpretation why adding the softmax making this work? So
Yeah, so there's this counting thing. So softmax help in counting stuff. So there's actually building Merrill's papers on this. If you have counting and look back, it's almost you can do everything transformers can do. So there's those kind of theoretical papers which I don't know all the details. But here we do the same thing, right? So we find this thing, maybe it's helpful, and we don't need maybe full attention layer. So we can use this static attention layer, and maybe it's already helpful as good as attention. And speed-wise, because we don't calculate any dot products here, so it's a constant time efficient than the normal attention. And memory-wise, it's also 1/3 of linear attention because we don't have query key values. So there's some fractions, but that might be helpful if you train very large models. And what we did is we added these models, we inserted these layers into other models. So let's say we have a Mambo model, we replace the second layer of Mambo with this layer. And maybe just say, only learned thing here is this W, right? So there's only one learned parameter here. And what we see is actually, sorry. What we see is if you add these layers, and the notation here is, so you have one here that says it's a 1 gram head. And this means I added one 1 gram head and one 2 gram head. And then 1, 2, 3. So this kind. So when you look at this, you see if you had just 1 gram head, which does this associative recall thing, look the same character and kind of attend to that character. It's actually not that helpful, but if you have 2 gram head or 3 gram head, they become exactly same as transformer in this task.
Yeah, I'm wondering, wouldn't you directly insert that layer into a pre-trained model like that, or you do some further fine-tuning?
So for these experiments, all the models are trained from scratch. So on this in-context language learning task. I will come to the language modeling part after this. Yeah. So, but what it shows, this is sometimes called induction heads in the literature, the 1 gram head. It's not actually that helpful if you just have that for this task. But if you have 2 gram, then I think it becomes same as transform. So we kind of show transformer is maybe implanted in this heads, and this is the only kind of the most important reason that the transformers are good at this task, right? So, okay, so let's move to the exciting part. So we said we can study these model problems, we can do this analysis, right? But for what, right? So we want to have something useful, right? So the question is, does the findings from these model organisms or these in-context language learning synthetic tasks actually transfer to the real models? So here we actually take large transformer models, large RedNet models, and we pre-train them. So we pre-train them on real language modeling tasks. We train our language models, but we added these layers to them. And so these are hybrid models. And what you see in like all of these rows is they constantly improve the performance of models. They even improve the transformers models performance. And maybe the difference from previous experiment, we added two modules here. Like we added like 1, 2, 3 gram heads at the beginning of model and 1, 2, 3 gram heads at the end of the model. And another important thing here is actually induction head is not enough. So even for language model, so like we show it's not enough for in-context language learning, but it's also not enough for language model. So when I say induction head, it is this. So we only use this like 1 gram matching. And it's only improves 0.7%. But if you look at this like full module, it improves 2.6%. So yeah, this is, I think, like the most exciting results with this. And we are kind of like in the stage of like scaling these models. So I'll come to the questions, but like just to give like a little bit future work, and then we can discuss these results. So this like model organism thing is nice, but we only model the in-context, so inference time of these models. So we only model the test example. So we didn't model actual pre-training data of the language models, right? So in all of the model problems, we meta-train a model with similar tasks, right? But in the actual language modeling, we have like multiple tasks, independent tasks. So we need a model for pre-training data, and there's some work on that, like this like Bayesian explanation paper has like a mixture of hidden Markov models instead of single hidden Markov model doing test time. And there's like paper from here. They actually have like 2 task groups, like which are different in the pre-training, and test time you only have a single task group. And maybe one more future work, we are kind of working pre-training with these synthetic tasks. So we show that the n-gram heads are helpful, but we can also go to the direction that we can use these synthetic tasks during pre-training and kind of induce these like language learning biases into the models, and so that we get even better language models. So yeah, thank you. And these are the conclusions. And if you have any questions, we can discuss more.
Yeah. So do you mind go back to the n-gram head part? So do we, no, can you go to next?
Yeah, I'll do. Give a second. Just delays.
Yeah. So from this, can I view as restricting the kind of the model space for the attention, because originally you had it to be tunable for all parameters, but here you kind of restrict it to certain kind of
Yes
constraints. So this kind of, by enforcing this type of bias, you kind of get better performance.
Yes.
Okay.
But you don't restrict them all, right? We add them as additional layers. So like there's still like original self-attention layers, or there's like original model. Actually, one thing you can do, you can insert them as additional heads in the multi-head attention. Let's say you have like 16 head attention, you can add like this 3 head, which only does this, which is like kind of, we are working on it. So I think that might even like be nicer architecture.
Okay, that makes sense.
Yeah.
Yeah, I'm wondering, do you have some personal opinion about the downside of transform? So in my opinion, the downside is just cognitive complexity, and let's say NVIDIA has more and more CUDA kernels, so that the cognitive complexity can be distributed among more processes. So at that time, is there any downside for transformers?
Yeah, I'm not sure. So like from these experiments, what I find is transformers are really good, but maybe like adding these attention heads actually improve transformers a lot too. So maybe like kind of like having some inductive biases on top of transformers, like little inductive biases, like restricting the attention to n-gram tokens might be helpful. Yeah, but otherwise seems like that's the best in these experiments.
Yeah, but do you think
yeah, I think it will go. Yeah, I think like kind of, I don't expect to change so far, but maybe they are good for like these kind of copying. But let's say if you have like continuous inputs, like if you have like visual inputs, let's say with resonant features to these models, maybe MAMA is better. So like there might be other domains these models could be better, but I think like this kind of like reasoning and token space, I feel like these models are really good, but I don't have any others.
Yeah, do you think like adding such architecture, as you said, it will include the inductive bias, will such inductive bias to harm other tasks like natural language?
Yeah, so one thing I expect these heads to be maybe harmful is like repeating, because like what data does, like attend to similar tokens, right? That comes after the same token. So maybe it will repeat. There was a problem with language models when they were small. Like they tend to repeat, like like after some length, they say the same sentence again and again. Maybe it will kind of like make the models like that more. So like also like we just showed the perplexity improvements, right? We didn't test whether these heads improve actual like few shot learning performance that I showed in the beginning of like this presentation. So there's many more things to like look at in this direction. Yeah.
Okay, so I want to get this straight. Like, so you find these n-gram heads, which it's completely hard coded, right? Like you're just using the definition that you have given in the previous slide. You're like inserting these n-gram heads into existing transformer models.
Yes.
Like, in this.
Yes.
And then you're running like your standard like pre-training.
Yes, like language model pre-training.
Like the n-gram heads are still being trained in some way.
Yeah.
They start with some like initial state.
Yeah, like there's one projection parameter that is trained. Yeah.
So, yeah, I guess it sounds to me like that sounds to me like there's evidence that like initialization matters to some extent. Right? Like,
but the attention is still static, right? The attention doesn't change, right? Attention is static in the n-gram heads, but the projection parameters are trained. So there's like two flavor there. Like one is like something is static, one is like good in. It's not good even like projections random initialized. So
yeah, but the projection is going into like you're applying the projection first, and then you're doing the n-gram.
Yeah.
Oh, sorry. How exactly do you insert these n-gram heads, let's say in a transformer? Like, do you replace a layer or you?
Yeah. So what we do is we try to keep the parameter size same. So original full self-attention layer, like one layer of transformer has like 12D square parameter, including MLP. What we did is like this, like 1, 2, 3 block has 60, I forget, but let's say 60 square, and then we have an MLP layer after that. So basically we just replaced one layer with this, so that they actually have the same parameter size, so we don't change the parameter size of the model.
Nice.
But there's like other options. Like I said, I think the best thing is adding them as multi-head, attention, like extra heads.
Yeah, for this one, I'm wondering whether, what's your intuition of that it will help more than actually train the head, right? Like why a fixed, basically because we know the transformers from what you saw can represent these n-grams, right?
Yeah.
So maybe it would make sense to add as extra heads higher order n-grams that the transformer may struggle to learning, or what's your intuition, like that it would be more helpful than just have
higher heads are definitely helpful, and like what people saw in actual language models is induction heads. Like they saw like these 1-gram heads in actual language models, not like the ones that I synthetically trained. But people didn't discuss much like 2-gram heads, like 3-gram heads. So, and I think that shows the like kind of benefit. And the reason probably is like, transform can learn some of these from data, right? Like pre-trained data. Actually, they learn 1-gram heads. But like once we initialize them with these, maybe they need to learn, they can learn other stuff, right? So they already start like good inductive biases, so they can learn some other skills that that uses these sets.
Thank you.
Any other questions? If there is no other questions,
Yeah,
then